Alright guys, in this video I'll be discussing about bias variance trade-off. What is bias, what is variance and trade-off? Right, so before beginning our discussion, we will take a closer look at machine learning basics. So first you have something known as the dataset, which is nothing but a set of paired values of x's and y's. Right, you have n such values, means I goes from 1 to capital N, let's say. Now given this dataset, there exists a function f. There exists a function f that explains the relationship between the x's and the y's of the dataset. In other words, it explains the behavior of the dataset. Right. Now this is a function. Now what is your goal? Your goal is to find out that function, because this function is something, it is out there and you don't know it. You cannot pin it down mathematically. You don't know whether this is a sine x, whether this is a log, whether this is a function of log, tan. You don't know that, but you believe that there is a function that explains the pattern between the dataset. If there was no pattern, then it's pointless, to apply machine learning. So having said that, your goal is to find this function. Now how are we supposed to do that? With the help of something known as hypothesis set, which means you build your own hypothesis, let's say h of x, and in believing that this will, expecting that this will, h of x will basically explain the behavior of the dataset, just like f of x, right? Which means you're trying to approximate f of x using h of x, right? So that approximation, that how far is your hypothesis from f of x, will be given by a metric called the square distance, right? This will tell you how far you are from the f of x, right? And this is for only one point. So if you consider the entire data set, you have to take the average value, which is basically the expected value. This entire thing is known as your MSE loss, right? The mean squared error loss. Now why am I saying this? Because what has this got to do anything with the bias and variance? Just hold up, just bear with me. Well, can I write this entire expression as h of x minus f of x, h of x minus g of x plus g of x minus f of x, right? Because minus g of x plus g of x will cancel each other, and I have the intact expression, the previous expression. Now what is this g of x? Well, g of x is nothing but the expected hypothesis, means the expected value of h of x. It is the expected hypothesis. Now what is the meaning of this entire thing? I will explain that later with an example. But first let us evaluate this one. So this will be, this is my a, this is my b, a plus b whole square. So this will be what? H of x minus g of x whole squared plus expectation of, because expectation of, let me just write this down, expectation of a plus b will be equal to the sum of individual expectations. So basically expectation of a plus expectation of b, right? Similarly, this one will be my g of x minus f of x whole squared plus expected value of twice h of x minus g of x times, I have here g of x minus f of x, right? Now focus on this expression, this one. And there is another thing, which is the expected value of a and b. If both events are independent, then you can write this as the multiplication of the individual expectations, right? This is b. Sorry for my handwriting. Yeah. So having said that, what I can do is I can take the individual expectations, right? And 2 is a constant, this will come out. Now this thing, focus on this thing, then I can write this as expected value of h of x minus expected value of g of x, isn't it? Only this part, this portion. Now focus on this one. Now g of x is basically the mean hypothesis, right? So the mean hypothesis, the expectation of the mean will be the mean itself. What do you mean by that? Consider a simple example, three numbers 1, 2 and 3. Now what will be the mean of this one? The mean is, the mu is basically 2, because sum of the three numbers is what? 6. 6 by 3 means the number of numbers, so that is my 3. So 6 by 3 is 2. So basically that is my mean. Now what is expectation of mean? Right, expectation of mu, that is nothing but mu itself, because mu is a single number. So applying that logic, this entire thing will be my g of x, and this one, which is e of g of x, expectation of hypothesis set, is my g of x itself. So this is also g of x. So g of x minus g of x, what will it be? What will it be? It will be 0. That means this entire expression will go to 0, since this is multiplied, and anything multiplied with 0 will give you 0. So this expression will, like, yeah, sayonara, we don't need it. So we will focus on the first two, this expression and this expression, right? Now let's focus on this one. Sorry, yeah, blue, I need blue. So this one, so this is a target function. It is a very specific function. This is what? G of x is the mean, right? The h of x is a random, you can consider that as a random variable, but okay, that's a different concept, but yeah. So g of x and f of x, right? So these two are functions, in identical, not identical, sorry. These two are basically, g of x is a very specific function, the mean, the hypothesis, and f of x is a function, the target function, right? So what am I saying is, expectation of a constant is the constant itself. So similarly, this will be nothing but g of x minus f of x whole square, right? Well, this entire thing, this whole very idea will be cleared if I show you the example, which I'll be soon. Now that is it. Now this one, if you take a look at this one, this is nothing but h of x minus expected value of h of x whole square plus. Now this entire thing, this is known as variance. This is your variance of the model. This one is the bias, and this two equals, summation of this two is your MSE. This is your MSE loss. So that is why I started off with this expression, right? Now bias and variance. So this bias means how far your hypothesis, your mean hypothesis, is from the target function. And this one, variance is basically how far individual hypothesis is from the mean hypothesis. So basically variance means the spread, how spread they are, right? And variance also determines the variability of the function. So this much is I have clear. Let us see an example. So in this example, what we are trying to do, I have created a dummy data set. So this is my dummy data set, right? And this is my function. So this is blue points are my data set, and green one, the green is my function, my f of x, the target function. So let me just write it down here. So green is the target function, right? Nice. So green is my target function. So we are trying to approximate this f of x function with two hypothesis set. First one is by a simple constant function, right? h1 of x equals w1. It's just bloody simple constant. So what we will do, the idea is basically you will split this dataset into, since we are doing this with 4 functions, 4 hypotheses, so we'll split this entire dataset into 4 different parts, right? And we will, on every, see, this is this sine curve explains the behavior of the entire dataset. So if you split that dataset into 4 different parts, then also this sine curve will explain the behavior of all those 4 different datasets, right? Derived datasets. So that being said, we'll split this into 4 different parts, and that will look something like this. So this is your, so one part is all the red points, and that is all the green points, and that is the blue and the oranges, right? So that is your dataset, and on each of these dataset we will apply machine learning problem. We'll try to approximate sine curve using this 1, 2, and 3, 4 this specific hypothesis. Now this is one specific hypothesis, right? The moment you give here the z, instead of 0, if you write here some variable, that is your hypothesis set. Anyway, so this is a constant function, as you can see. Now we will try to approximate the sine curve with a constant function. So for hypothesis 1 is the blue one, so this is the hypothesis that you get, right? Then the red one, similarly for h and everything. So the red, the green, and the yellow. So these all are trying to approximate what? This black f of x, the target function. Now we will take the mean hypothesis, right? Remember, the mean hypothesis is denoted by the letter g. So g is basically the mean hypothesis. As you can see, h1 of x plus h2 of x and so on, divided by the number of hypotheses. So mean hypothesis will look something like this. I believe the mean is determined by, yeah, so mean hypothesis is given by this black line, and the rest are individual hypotheses, right? And the sine, the curve, and the sine function given by the sine curve is my target function. Now we'll only plot the target function and the mean hypothesis. So this is what it is, and the distance, there's a distance between these two, the distance between these two is my bias. So we'll calculate the bias. As you can see over here, the variance is basically, let us check the formula of variance, right? Variance is basically, yeah, hypothesis, individual hypothesis minus the mean. So individual minus the mean and the whole square, and you do this for 4 of them. So, and you get it, right? So this is your bias, and this is your variance, and if you add them, this is the total loss, which is 2. Now we will try to approximate the sine curve with a more higher model, which a higher complexity model, and that is basically a straight line. So this is what it looks like. This is my 4 individual hypotheses on the dataset, and this is the expected hypothesis. We have repeated that step, and we have calculated the bias. This is our bias, and this is the variance. So let's take a closer look. So yeah, so this is the bias and the variance, right? So this is due to the straight line, and this is due to my constant function, right? Constant function. So can you see the difference, that when we use a straight line, a higher complexity model, then the variance increases and the bias has decreased, you see? So that means if you increase the model complexity, so that means if you just draw a graph, simple graph of the model complexity, so here it goes, then the bias decreases. So this is your bias. The bias decreases. As you can see here, bias was 0.49. Here it has gone down to 0.39. So, and the variance increases, and also the variance increases. So this is the variance. So variance increases, right? So if you increase the model complexity, then the bias will decrease and the variance will increase. Now, isn't that so? So if the variance increasing means your data set, like your hypothesis, the model has variability means it can vary itself in order to fit the data. So in this case, if it has a high variance, this is known as overfitting. This will overfit the model, means it will memorize the model so well, that it will poorly perform on the unknown dataset, which means the dataset means the generalization capability of this model with a high variance will decrease eventually. It will have a poor generalization capability. Similarly, in this case of a high bias is no matter what function you give it, what dataset you give, it will basically use a straight line, or rather a constant function to try to fit the model. So it has a high bias. So it is analogous to this example. So let's take an example. You are a student and you have an exam, right? You're trying to take an exam and you have only read 10 questions because you believe that only those 10 questions will come and nothing else will come. So it eventually will perform poorly on the test, right? So that is the condition of, rather that is a scenario of underfitting. So if the bias is more, this is underfitting. I'm writing like a doctor. Yeah, underfitting. So this is basically underfit. Scenario is underfit. Now what is the sweet spot? Now this one, you see, this is the G spot, means good spot. So this is the good spot, right, where the variance and bias are lower, like just right. So this is the just right fit. That is the just right fit. So this was all about biases and variance. Now if bias increase, then you know that your model will not learn from the dataset at all. And if variance increases, then model has memorized the dataset, which you don't want. You want model to find the pattern, to memorize the pattern, not the dataset. The goal is to make the model memorize the pattern and not the dataset. So that is a pattern, means basically the behavior of the dataset, which is explained or determined by the target function f of x. So I hope this video was useful. Anyway, all right then. Hope you have a great day. Adios, folks.